Thank you very much. Well, it's a pleasure to be here. And I thank the organizers for inviting me. I have to confess, it's both an honor and complete novelty for me to speak at a conference of this event. So I had no idea coming here whether most of the audience would, these phrases would be familiar, completely unfamiliar. So I tried to err on the side of accessibility. So I apologize if it's too pedestrian, but let me know just by eye contact. So I actually won't dive into quantum entanglement just yet, and I'll try to build up towards this emergent space-time through telling you a bit about holography. And the story actually starts even further back with something you'll probably consider even more esoteric, but it's my favorite object in physics, namely black holes. So, as you know, 100 years ago, Einstein formulated his beautiful theory of gravity, general relativity, which says that gravity is the manifestation of space-time curvature and matter enters pure space-time. So black holes are a robust prediction of the theory formed whenever you can get sufficient amount of matter into a small enough region. And in nature, this actually happens all the time, typically when a star has reached the thermonuclear recording phase and collapses. So once the black hole is formed, nothing can ever escape, as you can see by these light cones, any physical object including the light cones. And the defining feature of the black hole is an event horizon. Now, in fact, once inside, you're also compelled to come to this so-called curvature singularity, where the laws of general relativity break down, and we need to replace them by something else, quantum gravity, which is still framework that we're seeking. But in the meantime, so initially, for half a century, people didn't really believe black holes as physically sensible objects until astrophysical observations caught up and propelled the field into golden era of black hole research in the 70s. And people learned that black holes are much more than just amazing objects out there in the universe. They're very powerful theoretical laboratories. And they, in fact, underline various dualities that we have been learning about quite recently. So you'll see black holes sort of re-emerge as giving us insight into much more mundane, sort of almost everyday type systems. So the first hint of that was through observation that the laws of black hole mechanics actually very closely mimic the laws of thermodynamics. And so two important quantities that come into play is that area of this event horizon, this point of no return, and that weird quantity called surface gravity, which is like a force per unit mass to hold an object just at the horizon if you measure it out from infinity. Okay, so you can see if you write down the laws of black hole mechanics and the laws of thermodynamics, they're very similar. In particular, the surface gravity takes a role of the temperature, and the black hole horizon area takes a form of, is analogous to entropy. And in fact, this is more than analogy. So initially people said, well, okay, these are very similar to identify temperature with surface gravity and entropy with area. And there were Gedanken experiments which motivated why black hole entropy should scale with horizon area, basically preserve a second law of thermodynamics in nature. But Hawking famously calculated that black holes actually radiate semi-classically with a temperature that's indeed given by this by surface gravity, and fixed the constant of proportionality. And so that allowed us to fix the constant of proportionality for the black hole entropy in terms of its area as well. And I very much like this formula because it illustrates what are all the branches of physics you need to actually understand why there is a relation. And in fact, it feels like we need basically all of them. But it's still an outstanding question. We're used to entropy for statistical mechanics measuring, the number of microstates. And well, it's a big question and a good testing ground for a quantitative theory of quantum gravity to answer where are all these black hole microstates. So just to give you a sense of scales, for a solar mass black hole, which would be about 3 kilometers big, it's extremely compact, the Hawking temperature would be something like 10 to the minus 7 Kelvin, and the entropy would be something like 10 to the 77 also units. And so the number of microstates is, as I learned at lunch, it's 10 to the 77 number, so humongous. Okay, so one of the lessons that this type of formula taught us is the so-called holographic principle. So you can start by asking, well, how much information could you store in a given region? Okay, and if you don't have, in general, you can sort of start calculating. You have, say, one book, you have some amount of information, 2 books, that's what you have twice as much information, you keep going, and the information scales, of course, linearly with volume, just extensivity of entropy. But that's ignoring gravity. If gravity comes into play, eventually, no matter how little you would pack in each box, the whole thing gravitationally collapses. Right? And then, of course, this is not realistic for boxes you pack your favorite impermanent books in, but we know that for black hole, the entropy scales with area rather than the volume. Okay, so that's a novelty. And in fact, that leads to the holographic principle, which tells us that somehow we can describe everything inside the box by just the amount of information that would live on its surface. And the guess is that, well, there should be some theory which lives in lower dimensions that would capture everything, all of the physics that's contained inside the box. So that's the holographic principle. And we have a very beautiful concrete realization of that, namely the gauge gravity duality, or the ADS-CFT correspondence. So before I delve into that, just to sort of, tell how I think about duality, what we mean is just that you have the same physical reality described by 2 different descriptions. So most of you are familiar with some form of duality or another. And I like this Asia picture which sort of illustrates part of that idea. Basically, the variables that you use on one side become less and less applicable as you go away from this quad. Typically, increasing the strength of coupling, your fundamental degrees of freedom become less and less distinct as they become to interact strongly with each other. And as you ramp up the coupling all the way to infinitely strong coupling, the surprise is that instead of completely losing control, there is a new emergent picture which looks weakly coupled, but now in completely different variables. So that sort of thing is happening in this gauge gravity duality. And well, most properties that you might have thought sacrosanct are actually lost by passing to another duality frame, much more so than you would have guessed from a picture like this. Okay, so the gauge gravity duality was initially called ADS-CFT correspondence, formulated within the context of string theory by Miroslaw, but it almost 20 years ago, but it applies to a much broader context. So it transcends the original sort of string theory context. So it says that string theory, which among others is a theory of gravity, is describing exactly the same physics as a certain gauge theory, which of course doesn't have any gravity, and it happens to be a conformal field theory. Now, the 2 theories live in different number of dimensions. The string theory lives in what we call bulk of a certain space-time called anti-de Sitter. It's like an analog of a hyperboloid when you put in time. It's a maximally symmetric negatively curved space-time. The gauge theory, the field theory, lives on the boundary of this anti-de Sitter space, so less dimensions. So in the early days, people thought of this in sort of a SUPCAM analogy picture where the string theory is the SUP inside and the gauge theory is just a label. But unlike the ordinary SUPCAM, here the label is everything. Okay, so because the 2 theories live in different number of dimensions, we call this correspondence holographic. Of course, it has nothing to do with actual holograms. And in fact, I think the better analogy would have been a stereogram. where you see a 3D image coming from this due to the sort of correlations between the pairs of these splotches that your eyes interpret as parallax. But in the real idea CFT, it's of course infinitely more complicated with correlations between everything, and you're having a sensible picture in the CFT on its own, like quite different from the higher dimensional holographic image. Okay, so the space gets completely scrambled between the two sides, but it's not random. It's very finely adjusted so that things make sense and actually come out just right on both sides of the duality. And to give you some sort of a sense of how this manages to conspire itself, well, the basic question is what happened to this extra bulk direction that we have lost in the lower dimensional picture. And it's telling just to, part of the answer already comes from the spatial geometry. So if you look at, this was a space-time diagram, you just look at the spatial geometry, this is the boundary. And each of these fish would be the same proper size. So you would have to cover infinitely many of them to get to the boundary. And it also, as this Escher picture nicely illustrates, there's no sort of preferred origin to the space-time. You can sort of translate things around. And so the mapping had better respect that sort of symmetry. And so this radial direction should come somehow from a scale size on the field theory. So in particular, if you want to describe some point in the bulk from the boundary observables, it should be delocalized commensurately with how deep it is in. So near the boundary it's small arcs, further away from the boundary it's bigger arcs. And then actually this picture also illustrates another nice feature that a same point can be encapsulated in many different ways. And in fact, recently that has been sort of thought about in an quantum error correcting code type language. So this correspondence also gives a nice intuition. For example, if you drop a particle in bulk from near the boundary, it will fall inward just by feeling the gravity of ADS. On the boundary, you of course have no gravity, but there things want to thermalize and spread out. Okay, so this is very nicely implemented. You can follow it to quite a bit of detail. Okay, now different so you can excite the geometry, as I said, in gravity. Matter back reacts on the space, the curved space-time, so you can put stuff into ADS. So if you don't put anything, that gives you a vacuum state, but you can excite it, and maximum excitation would correspond to collapsing a black hole in the bulk. And on the field theory side, that's just thermally exciting the state. It's a generic end state of, putting in some high energy thing. But we can also see how fluctuations around that behave, and we can map them on the two sides, and you can sort of, by looking at the sort of horizon response properties, you can read off the transport coefficients in the field theory fluid. And in fact, you can do this even at a nonlinear level, which is something called the fluid gravity correspondence, where the dynamics of a black hole in the bulk mimics the dynamic of fluids. And Einstein's equations actually contain the lower dimensional Navier-Stokes equations that govern that behavior. So you can generalize this from the original conformal fluid context, relativistic conformal fluid context, to quite a lot of stuff, and apply it to many areas. Okay, so the gauge gravity duality has had many applications. There have been more than 10,000 papers that refer to Molesina's original paper now. And basically the reason is, part of the reason is that you have just one simple object in the bulk, the black hole. We can dispense with all the stars and stuff. But there's a huge variety of systems that are even experimentally accessible on the other side. They're not often precisely dual, or mostly they're not precisely dual, but they have certain qualitative features that are shared by physics read by the black hole. And so this correspondence has been invaluable both to study these strongly coupled quantum systems, which is hard to do directly, by working with higher dimensional gravity, which is much easier, and on the other hand, by sort of understanding some aspects of a field theory, albeit strongly coupled, to ask about quantum gravity in anti-de Sitter space. So this is a large range of applicability, this, from ultra cold Fermi atoms to quark gluon plasma, so spanning 20 orders of magnitude in temperature and many more in pressure. And the basic reason is that there's various universal properties. For example, the shear viscosity to entropy density ratio, which sort of characterizes the internal dissipation, behaves in a qualitatively sort of similar way. And in fact, the holographic bound that tells you, how low you can get to in systems which have a holographic tool is nearly saturated by both the very hot quark gluon plasma and the ultra cold Fermi systems. Basically, things that look as much conformal as you can get. All right. So let me now get to the main point of the talk, which is this entanglement, and in particular, the measure of that, the entanglement entropy. So the path in ADS-CFT has taken sort of two main directions. One was this applied ADS-CFT, where you study some known system by doing a calculation in the dual. And another was sort of trying to understand the fundamentals of this correspondence. Why does the mapping work, and how does it work sort of in more detail, so that we can actually realize the hope of understanding, really sort of seeing the connections and taking full mileage out of them. I think so far, despite the 10,000 papers, I think we have really seen just the tip of the iceberg. I think the first one is really holds much more. But we need to understand this dictionary much better for understanding that. And curiously, the subject of entanglement entropy has cropped up from both of these directions. And the most intriguing aspect of that is that it has gives us some insight for quantum gravity. Okay, so what is entanglement? Well, I would think of it as sort of the most non-classical manifestation of quantum mechanics. It's a property of any quantum system, which sort of tells us that, which is present in the state of the global state of a composite system cannot be written as a product of the states of the individual subsystems. So it's also illustrates this, the best possible knowledge of the whole does not contain the best possible knowledge of its past, and it has confused people since the beginning of quantum mechanics, and still lies at the heart of many of the pressing paradoxes today. But the more modern view of entanglement is as a quantum resource for tasks that can't be completed using just with classical resources. And this has made entanglement a central feature in many diverse fields, not just quantum information, in quantum computing, but quantum poly systems and quantum field theory and so forth. And over the last few years, it has been increasingly more clear that this is also very crucial in understanding, or provides very big hints in understanding connections to geometry. So just a brief review. A nice measure of entanglement is the quantity known as entanglement entropy, which sort of characterizes how much, if you had an access to only part of the system, how much, what would be the sort of von Neumann entropy of that part. So you form a reduced density matrix by tracing out over the unknown bit of the system, and you form the von Neumann entropy, which is like a quantum analog of the Shannon entropy, out of that. And so this is well defined if you can divide up your Hilbert space into the subsystem of interest and the rest. So if you have a field theory, a local quantum field theory, one natural separation of the Hilbert spaces is simply by spatial regions. You delineate some spatial region, so this is a space of a field theory, and suppose you only have access to this region, so you can ask what is the entanglement entropy of this region. And people have used this quite a bit to understand various phase structures and so forth. And it has been a very nice diagnostic. However, it's a very hard to deal with quantity. It's a sort of non-local quantity. It's very intricate. It's sensitive to environment. It's very difficult to measure and calculate, especially in strongly coupled systems. But we have been as holographers, we have been trained to always ask, if you have a hard question in strong applicable field theory, does ADS-CFT come to a rescue? And we even have been trained to expect that the answer is yes. And so what would it entail here? Well, you would want to ask, put this field theory on the boundary of some bulk, and ask, is there some quantity in the bulk that sort of mocks up this entanglement entropy in the field theory? Now, I have said that entanglement entropy is a very intricate quantity, and we have already seen that the mapping between the bulk and boundary is very intricate. And so you might say, well, there's no chance, it's doubly complicated. But in fact, the answer, does ADS-CFT come to rescue, is yes, a resounding yes, and in fact, it's better than that, it's described very simply, just geometrically. Okay, so the prescription for computing entanglement entropy is to take a certain surface in the bulk, a minimal surface, one that has the smallest area, so it's like a soap bubble, that ends on the boundary of this region, and compute this area, this proper area. So that's the prescription. And it, of course, depends on the bulk space-time geometry, which tells you what state you are in. That definitely the entanglement entropy depends on. And it's a simple quantity that includes this very complicated but very crucial quantity in the boundary. Okay, now, let's see, 5 minutes, right? Okay, I'll keep.
Yeah, you have like 8 minutes.
Okay, so far, the prescription that I mentioned before was valid only at a single snapshot in time for a static situation. But of course, the entanglement entropy is valid even more robustly for time-evolving configurations. And so we have to do better with this prescription. And you can indeed do that, and big guidance is to be, not tie yourself to any coordinate system, which is just our choice, but rather to have a well-defined sort of geometrical quantity. And so in Lorentzian in geometry with time, the problem is that the minimal surface doesn't have any meaning because you can always minimize areas arbitrarily by using time direction. And there is no natural sort of single time slice because there's no geometrical quantity that would capture that. It's sort of coordinate dependent. And so to sort of covariantize this, to have a well-defined prescription in time-dependent situation, one natural candidate is to just promote this minimal surface at a constant time to a simply extremal surface that is an extremum of its area rather than a minimum. Okay, so that seems to work. So this is a new prescription which looks pretty much the same, but is valid now for equally robustly as in it's defined in the field theory. And there has been, although there is no proof for this, there has been a large body of evidence. And nicely, it satisfies various very non-trivial properties of entanglement. So this prescription geometrizes what entanglement is, and the properties that any field theory have to satisfy in terms of entanglement, and which might be very hard to prove directly on the field theory side, are manifested almost trivially on the bulk side. So one of the things that's manifested trivially is if you have pure state, entanglement entropy of a region is the same as of its complement. Well, that's obvious because the extremal surface just is anchored on the boundary, so it's can't distinguish between the two. It has to be entanglement has to be entropy has to be a positive quantity that's also manifest. There is a relation called sub-additivity, which is also pretty manifest. In fact, there's a stronger relation, which I'll do for you, which is strong sub-additivity. So instead of entanglement entropy of sum of entanglement entropies of two regions is bigger than the entanglement of the union, you actually have is bigger than the entanglement of the union plus that of the intersections. And this is a very trivial proof in the bulk geometry. So in the bulk, you're just computing these areas. Oops, my point. You're computing these areas of the surfaces, and you want to see that the area of the red plus the blue curve is bigger than areas that would correspond to the intersection and the union. So you can split up that the left curve into two like here, and then because the actual minimal surfaces, you see that that this inequality is satisfied. Okay. I hope the lack of the pointer didn't harm this explanation. Okay, so that was just an illustration. Now this was in the simpler context of not time-dependent situations, but you can generalize it to time-dependent things as well. In fact, you can go much further and understand what other sorts of inequalities that we don't really have handle on in general field theory would follow trivially from just the fact that you have this prescription in the bulk geometry. And there's a whole tower of these relations, which people came to know as the entropy code. And in fact, there's also relations that hold, like this monogamy of mutual information, that hold only for systems that have a holographic dual, but not necessarily in general. And so this is an advantage of answering part of the question, given any field theory, can it have a holographic dual? Can it have a dual description in terms of some gravitational system? So if it doesn't satisfy these types of relations for its entanglement entropy, then the answer is clearly no. So it's one diagnostic for this type of question. So let me just skip this in interest of time. There's further you can get, and I'm going to speed up very much just to finish on time in a few minutes, so I'll also skip most of this, but the upshot of this slide was that a relation that is sort of a strong subadditivity is like a convexity property. It's very much akin to sort of the second law of thermodynamics. And this pretty fundamental relation now tells us something about the field equations that govern the bulk, the Einstein's equations. So there has been lots of progress in that direction in the recent few years. And in fact, it has gone even further of asking, well, is space-time actually built out of entanglement? So Saskind and Maldacena had proposed that something that described by the sketchy phrase ER is equal to EPR, which stands for the Einstein-Rosen bridge of a black hole to an Einstein-Podolsky-Rosen type experiment with EPR pairs. There's a sense that those two are actually somehow fundamentally connected. That if you have geometries which don't implement any entanglement, they're not connected, but once you sort of maximally entangle them, they become connected. So I guess these diagrams don't make much sense to you, so I can answer, sort of explain that a bit more in the question session if you want to privately answer that. But the upshot is there is a sort of sense that space-time is somehow built from quantum entanglement. Okay, so let me just summarize by sort of a epilogue of how much our view of space-time has changed over the last 111 years or so. So we started with, of course, notion of absolute space and time before, and the special relativity told us, there's only space-time, which is a finite speed of light. Then with general relativity, we learned that this was dynamical quantity and it was curved and so forth. Then string theory told us that space-time was actually higher dimensional, it was fuzzy, it had very complex internal structure. Then with dualities, we realized that space-time geometry is not a fundamental quantity that can change in different duality frames. The topology can change. The fact that we have singularities can change. Dimension can change. All of these things can change. And holography told us that the space-time is somehow emergent from a non-gravitational quantum field theory. But what we don't yet know is exactly how. And the recent hints have been that, well, quantum information theoretic constructs have been playing quite an increasingly significant role, and so perhaps space-time emerges from quantum entanglement. Okay, so there's much of an exciting times ahead. So, thank you.
We have plenty of time for questions and conversation. Yes.
How does the particle physics field react to what seems to be a proposal that that the traditional reductionist approach of particle physics might be evolving to an emergent view at the deep level, which is what I take your talk to be telling us. People all like this, or it's controversial, and what, how's this playing out within the people who do this, whose lives revolve around, whose intellectual lives revolve around it?
Sociology-wise, I think it depends on who you ask. Many people are very excited about it, and of course nowadays you do find many people in condensed matter physics or nuclear physics, high energy physics, sort of studying general relativity, not just for cultural enrichment, but for actually making use of doing calculations. And I think lots of people are very welcoming of that. I think initially the correspondence has been oversold to the extent that people said, well, you can now, any system in nature has a holographic jewel, including my bottle of water or something like that. So that's not the case. So many of the real world systems, especially things that don't have enough huge number of degrees of freedom, small central charge, those things are not described by a genuinely gravitational field. And I think there was some backlash from the initial sort of overselling. But it's answering this sort of question is a bit of a selection effect, because I'm mostly exposed to people from other fields that are supportive enough or interested enough to be sort of going through the same conferences I am.
Moving toward a second question.
So the universe is a de Sitter space, isn't it?
Yes.
So how can the holographic principle play any role in the universe?
It's also, as far as we see, macroscopically four-dimensional. So here, well, there are two answers to it. One is that the real-world systems that have similar features as what I have. Let me go back to the slide. To these types of things. These types of things are the things we're familiar with in, say, 3+1 dimensions. The black hole would be 5-dimensional. So our universe is in that picture is where gravity is unimportant, and is described by a higher dimensional black hole. In which case we don't really care that we don't live in anti-de Sitter, but we live in de Sitter. There's one more answer that I want to say, which is for this type of program of understanding quantum gravity, the essence of what happens at a black hole singularity, from understanding this side, we don't really care so much about the black hole being in anti-de Sitter versus being in de Sitter. We think that the singularities of our black holes out there can be resolved in the same way as singularities of black holes in a cosmologically distinct space-time. The properties of the black holes are still the same. And so for that, it also doesn't matter that the cosmological constant is the wrong sign.
Okay.
In both classical and quantum field theories in condensed matter physics, our most profound emergent phenomena principle is really organized around the renormalization group, which helps us describe spontaneous symmetry breaking and ergodicity breaking that actually only becomes real in the thermodynamic limit. The Sitter space is finite, and anti-de Sitter space is finite. And
that one is actually.
And the thermodynamic limit would be the limit of zero curvature, which means zero gravity. So there's no mass and no curvature, no gravity. So I'm just curious if it seems as if that would become a very subtle limit for you.
No, and in fact we are in thermodynamical limit. The small scale here would be sort of the Planck scale or the string scale, and that we can take large by taking the radius of curvature of anti-de Sitter large. So we are in the thermodynamic limit.
Well, I thought alpha squared, the isometry that defines your de Sitter space or anti-de Sitter space preserves a
It's a box of finite volume, but the number of degrees of freedom inside that box is infinite because we have large central charge. In fact, infinite central charge. So we are in the thermodynamic limit in slightly different sense.
The space on the surface is finite. The CFT is a finite.
It also has it's a CFT. Well, this particular thing is a superannular sphere with gauge groove, SUN. But for the gravity limit to be valid, we take n to infinity. And that's the thing that implements the thermodynamic limit. I should by the way say that this Archie flow is very beautifully implemented in the holographic correspondence in this scale radius duality type picture that I showed here. Somehow the organizing principle is precisely sort of this Archie flow is now just radial flow. And one of the reasons that the correspondence is so successful, I think, is precisely this more natural reorganization of the sort of constituents of the variables you want to talk in terms of. So whenever condensed matter physics gets stuck by not having a good quasi-particle description, ADS-CFT is powerful because that also doesn't have quasi-particle description. The organization is slightly different, and it's somehow probably more natural for how many of these systems are organized.
You have another question?
Yes, related to what you just said. Is this duality dependent on the partition you are making in the system? So if I have a different, because the entanglement depends on the partition. The partition between A and B, yes. So I'm asking what relation there is between the partition. If the partition is complicated, if I do a unitary transformation to another space, not real space, if I get the same duality space. So how does this transformation, this duality depend on the partition, on the particular partition I'm doing in the space? You understand? So the partition you were alluding to is real space.
Are you talking about the part where I was talking about entanglement?
I'm talking about entanglement, yes. I'm talking about the surface.
This is already before that. So before making the decision about what partition we take, there is already this correspondence between the scale and radius and all that. So that's independent of the entanglement entropy. Now with the existing mapping, we can take a more fine-grained quantity. We can now ask for a given partition, what would be a certain quantity like this entanglement entropy. So that partition we put in by hand, just as we would ask what's the property of some system we choose by hand here. So that's what we do on top of the duality. So I'm still not sure whether I'm sort of answering what maybe you can.
You have another question here?
This is just a question to you. It's my impression that ADS-CFT has been great for people coming from string theory, but it has been very bad news for those condensed matter physicists who've gone into that area. What do you think about that? In terms of their productivity and what they've actually succeeded in doing.
They don't really excite them the black holes.
Well, I don't know, people like
Oh, I know, these are my friends, but
Not anymore.
Well, I don't want to personify it, but it's my impression that they have people involved with. I've spent some time on it myself. It's been extremely stimulating in some sense. It's not clear that it's actually given us something that we can relate to the experiments and things we're working on. And so I think it's wonderful to bring people like Sean Hartnott in, and he starts solving Boltzmann equations and thinking about transport properties. That's great. But the other way, I'm not sure how well it works for us. I was curious what you think. I mean, you're coming our way.
I'm coming from the
So it's good for you.
other side.
But
okay, so
I mean, from a practical point of view, there's no dictionary there.
they're building
I
blocks.
find it inspiring, okay, and I've even got some papers where I talk about, we've got a toy model where we have time becoming a normalization group, but I've seen some very able people, not just the two you mentioned, who spent a huge amount of time on this, sync of their abilities.
You should ask them. I can't judge.
You can't.
Honestly.
Yeah.
Physicists, but you know, it's certainly okay. I think it would be a sink of time if you sort of come in with the attitude that I'm going to solve exactly my favorite lab model by this duality. I think its purpose is slightly different. It's very good in sort of classifying what can happen, you know, all the different quantum field theories you can have. It's good in sort of having a broad explanation for various universal quantities and so forth. So if you come in with sort of a mindset of sort of understanding those things, I think it's not necessarily counterproductive, but if you're trying to build up, you know, a model that more and more closely resembles some specific thing you have in the lab, then it becomes very baroque, and then it's not at all clear.
Okay, while Dan is asking the last question, I'm going to ask Miroslaw to get set up. Is that okay? Go ahead and plug in. Okay, go ahead.
I wanted to ask you two quick things. One, just to understand, I think I've seen it before, you had this plot of the shear viscosity over, I think, entropy. And is that a useful measure to tell how close you are to holography?
Yes.
Yeah,
It is
so-
because as it comes to 1/4π,
Right.
it's more and more indicative that the internal dissipation is governed mostly by quantum effects.
Right.
And so it's more and more close to here.
And so then the second question is maybe to flip it from what Piers said. He was talking about people who are coming from more a sort of field theoretic approach to condensed matter problems and trying to apply EDS-CFT. And I guess the question I would just quickly ask you is, to what extent are the numerical approaches using, say, the tensor network? Yeah. I mean, maybe that's too broad a question, but the tensor, which I know you're interested in, but the tensor network, tensor matrix, the tensor network normalization group and so on. That looks like a promising thing for condensed matter. Does that look promising for your side?
It looks promising for understanding the map better. So yes, people are interested in that just to understand how entanglement relates to geometry.
Okay, let's thank Veronica again for a I think we needed a martini.
Good afternoon, everyone. So I'm going to talk today about DNA and liquid crystals. But first of all, I have to thank ICAM for support, which leads to the collaboration between Penn State University and the research center in Jülich in Germany, which was actually the starting point to another collaboration with advanced light source in Lawrenceburg National Laboratory. And yes, here are the results with those with this collaboration. First of all, I think from chemistry we can get a lot of we can get a lot of new materials, and they are so proud that they can synthesize almost everything with very well defined properties. But not every time this is true, of course. But I think, especially in the beginning of 20th century, they forgot how much we can learn from nature. And yesterday, if you remember, the first talk was about actin polymerization, which is a very nice example of how we can get from nature to some other disciplines like physics or chemistry. And recently, 2 or maybe 3 weeks ago, I found a lot of these titles in many websites related to a DNA-based storage system, and which is another nice proof of how we can apply nature to some other applications. And this is related to DNA, which is a very complex system, but still we have to learn a lot how those molecules are organized, and especially in self-assembled materials. Not only non-electronic devices can be made with DNA. DNA is very important in our life, because otherwise we cannot survive without DNA probably. But DNA applications are also important in gene therapy or like disease screening. And the key point is to understand what is the self-assembly, what's the rule of self-assembly, and how we can control this process. And what is the chemistry between us and our results is this DNA dimer made with 2 DNA arms, 48 base pairs, and here we have 1 to 20 thymine in single strand DNA, which means that here we have 2 stiff fragments and flexible part between them. And what we can find out for the system which has only 1 thymine in single strand DNA, the behavior of the system is very similar to long DNA which is in our body. Probably everyone knows that DNA in our body is in liquid phase. And what you can find out is that this is nematic state, actually steady state, because this is a chiral molecule. And this texture from polarizing optical microscopy shows this chiral nematic phase. And supporting technique that we use for our studies was performed in cyclotrons facility, small angle X-ray scattering, which shows that for small concentrations, low concentrations, we have found a nematic phase or isotropic phase. But for high concentration, we have found this narrow peak, which corresponds to 2.7 nanometers, which is the distance between 2 helices, DNA helices. So yeah, and here you can see this wide angle signal, which is very narrow. And what we did, we did also a phase diagram. We hit our samples from 5 to 45 degrees Celsius, and for almost all concentrations starting, let's say, from 170 to 300, we can find nematic phase, or steady phase, or hexatic phase. Hexatic phase is the phase when molecules are organized here. They pack densely in hexatic order, in plane, of course in plane. So let's switch to the other system. And next system is made with 5 thymine linkage, 5 thymine in single strand DNA. And what we have found for high concentrations, here is tiny small peak, which correspond, this peak corresponds to the length of the 1 DNA dimer, which is around 60 nanometers. And for low concentrations, of course we find nematic phase. For high concentrations, we can find this lamellar phase. Here, probably you can see this tiny peak, which is here also, after integration. And wide angle peaks also is very narrow, which means that we have something more than regular Smectic A phase. Because we have also hexagonal packing in plane, which is, we call this Smectic B phase, which is very close to crystal phase.
Is the small peak the indication of the limit?
This means that we have lamellar phase, but this also means that we have in-plane packing. So it's more complicated than regular lamellar phase, yeah, let's say. So we did also a phase diagram, and I hope you remember that from previous system, we had from around 170 to almost 300 nematic or cholesteric phase. Now we have this cholesteric phase is suppressed from both sides, from isotropic phase and from isotropic side and from Smectic side. So now I will describe something. I will say something more about Smectic A and Smectic B for next system, which has 10 telomeres in single-strand DNA. This is very important image. This is a texture from polarizing optical microscopy, which show focal conic domains. If we have this kind of texture, it means that we have for sure Smectic A phase. So far, was released only few papers, and some people claim that they found out Smectic A phase, but they did not show any proof, strong proof that they have really Smectic A phase. This is proof that we have Smectic A phase. So, of course, we did also sex measurements, and when we increase the concentration, we see very well developed here small angle peaks. Of course, this wide angle peak also is changing, became much broader, sharper, and which means that we have also in-plane packing. So we go from Smectic A phase, which doesn't have hexatic packing in plane. Then we have something very, I'm not sure if you can see, but here we have a lot of peaks. Next slide I will show something, the integration of those three graphs. And additionally we have this sharp peak here, which means that additionally we have hexagonal packing in plane. And here, of course, we have both lamellar and hexagonal packing in plane. So, integration. This animation shows when we changed concentration from low to high. And what is interesting, here, this is Smectic A phase, lamellar structure. Then we have something strange, because here is splitting, I don't know why. I know, but next slide maybe. And here we have this, with this sharp peak here and lamellar structure. So let's go back again here.
Why are there two different?
And this is coexistence of two Smectic phases. One, which is like Smectic A phase, the easiest one, let's say, and the next one, and the higher one, which is like here, with this additional hexagonal packing in plane. So what we did also, we did temperature scan. And what we have found out that those signals disappear at 45 degrees. Here you don't see this wide angle peak, believe me, it's also gone. So you cannot see the signal at this temperature. Which means that really in low temperatures we have a coexistence of two phases, Smectic A and Smectic B, or let's say Smectic B light phase. And in high Smectic A phase, but in high temperature we have only Smectic A phase. So we did also phase diagram, of course, and what you can note, if you remember the previous phase diagram with a shorter linker, that nematic phase still is compressed from, but this time compressed from Smectic side. And because I don't have probably so much time, I will show only phase diagram for last system that we measure with 20 stimuli in single-strand DNA. And nematic phase is almost gone. It's compressed completely from both sides. Here we have only isotropic phase, or kind of existence of isotropic and nematic phase. And here we have only two Smectic phases, which in this case is more organized in this case. And this is something similar to short to small molecular short molecular dimers. When we increase the linkage, then nematic phase is gone and appear only crystal phase when the linker is very, very long. So what we can expect if we increase the linker in from 20 to, for example, 30 thymine in single-strand DNA, then probably the nematic phase will completely gone, will disappear completely, and we will see